try this yourself. It's extremely dangerous.
When we talk about atoms nowadays, we usually use diagram like this, where we've got a nucleus in the middle of the atom that has protons and neutrons, and then there are electrons around the nucleus. But of course, we didn't always know that atoms look like this. Scientists had to discover each and one of the subatomic particles one by one. The neutron here was the last of the subatomic particles to be discovered, and we are going to talk about how it was discovered. So, in the early 1900s, around 1910 to 1920, this is what scientists thought the atom looked like. It's not too different from this version, except that they are not having any neutrons in the nucleus. There are some clues that led scientists to discover neutron. First of all, some scientists said, look at the protons in the nucleus. Protons are positively charged, and like things repel. So when two positively charged, they will want to push away from each other. So they thought maybe there is something in the nucleus that keeps the positively charged protons together. Turns out that the things that hold the protons, positively charged protons together, is the neutrons. So there is a scientist named James Chadwick in 1932. He conducted an experiment on the discovery of neutrons. So James Chadwick took atom of beryllium or boron or lithium and shot alpha particles at it. So James noticed that rays are released from the atoms of beryllium or boron or lithium. So something are shot out from these atoms when they are hit by alpha particles. It is not sure what's coming out, but one thing for sure, whatever getting kicked out of these atoms, it doesn't have a charge. So it cannot be protons that are getting shot out because protons are positively charged. And it cannot be electrons because electrons are negatively charged. So they still don't know what it is. But here's the second part of the experiment. James Chadwick put paraffin, or in other words, is wax. They put paraffin in front of these rays that are shooting out from these atoms. And they discovered when paraffin got hit by these rays, protons are shooting out of the paraffin. These protons get shot out really fast. So whatever is coming out of the beryllium or boron or lithium is moving fast enough and heavy enough to bang into the atoms of paraffin and kick out the protons. So what they decide is that whatever is coming out of these atoms has to be about the same mass as the protons that are getting shot out of the paraffin. They know that the things that getting shot out of these atoms doesn't have a charge, and they have about the same mass and the same size of the protons. So this is how the neutrons are discovered. So actually, when the alpha particles hit these atoms, which is beryllium or boron or lithium, the neutrons are released out from these atoms. And when the neutrons move fast enough and hit the paraffin, the protons are coming out from the paraffins. So this is how the discovery of neutrons. Einstein showed in the theory of relativity that matter can be converted into energy. If the mass of matter is delta m, then the amount of energy is delta E. That can be obtained from the mass is given by delta E equal to delta mc squared, where c is the speed of light in free space. Unified atomic mass unit. Symbol U is a standard unit of mass that quantifies mass on an atomic or molecular scale. 1 U equal to 1 over 12 of the mass of atom carbon, and it is approximately the mass of one nucleon, either a single proton or neutron.
The difference in mass between the rest mass of nucleus and the sum of all isolated particles.
For example, the mass of a nucleus is 4.0015 U. Then we separate the proton and neutron of the nucleus, and the total mass of all isolated particles is 4.03 U. There is 0.0305 U different in mass. This is mass defect. Binding energy is the amount of energy required to take all the nucleons of the nucleus apart so that they become isolated particles. We already know how to find atomic weights by calculating the weight average using relative abundance. But where do this relative abundance come from? Now, let us take a look on mass spectrometry. By definition, mass spectrometry is a method of separating mixtures of substances into their components, turning them into beams of particles and then bending them with electricity and magnetism to make a kind of spectrum of different atoms that are easier to identify. In short, it is an instrument to measure masses and relative concentration of atoms and molecules. Now, let's just focus on the Bainbridge mass spectrometer. It has 4 basic regions, which are the ionization region, accelerating voltage region, velocity selector region, and the magnetic field region. In a mass spectrometer, a sample containing the atoms of molecules of interest is injected into the instrument. The sample is immediately vaporized by a heater, and the vaporized sample is then bombarded by high-energy electrons. These electrons are powerful enough to knock off atoms in the sample, which creates cationic versions of the sample. The ions will travel with a range of velocities and enter the same space between the metal plates, which are the velocity selector region. This region has cross-electromagnetic field, which means if the particle is moving too fast or too slow, they miss the opening on the other side. Now, let's take a closer look of how this can happen. An electric potential difference is applied across the magnetic field to produce a uniform magnetic field. So, we have the ions coming in, enter the hole here, and there is a parallel plate creating a vertical electric field. Let's say we have a positive ion here and negative ion here. So, of course this positive charge will experience a downward electric force, and we will also have a magnetic force, so it will face upward. We know that magnetic field equal to QVB. So, what can we do is select the speed and it will work like this. If the speed is too great, the magnetic force will be bigger. So, the particle will be deflected upward if they are going too fast and vice versa. If the particle is going too slow, it will be deflected downward. And if only the two forces are exactly equal, they will make it through this hole here and get into the magnetic field region. Now, if we want these two forces to be equal, we need to have this equation. FB equal to FE, so we will get QVB equal to QE. And we can cross the Q, so we will get V equal to E over B, in which B will be fixed. So we can select the V equal to E. Okay, now, how to find the direction of magnetic field? It is easy. You can use the right hand rule. So, we will get the direction of magnetic field is into the board, which is inside the velocity selector region. Once the ions reach the magnetic field region, they are deflected different amounts depending on their speed and charge. Ions that are moving more slowly, the heavy ions, are deflected less, while ions that are moving more quickly are deflected more. Think of the force you need to apply to accelerate a bowling ball versus a tennis ball. Well, it is much easier to accelerate a tennis ball, right? Also, the higher the charge on the ion, the more it will be deflected.